Hey, good afternoon, everyone. Good afternoon.
Good afternoon.
Afternoon, Professor.
Hi, good afternoon, Maria. Good
Hi,
afternoon,
Professor.
Alicia. Hey, good afternoon, Kelly and Claudia. Alrighty, so I see 10 people here. And then how many are there in the in today's forum? I have 10, so everyone everyone in the forum is in the collaborate and vice versa. Alrighty, so uh, you let's see. So in our last class, right? Uh, basically, we did present compounding and discounting. In other words, present, future value and present value. And I also told you last time that uh, the there are four unknowns, right? There are four unknowns that can be derived or asked from this question. In other words, this compounding formula or future value formula is the base function, right? It's the base equation, right? And based on that, um, and the process for arriving at the future value is called compounding, right? Uh, so future value is the unknown, right? And the other variables are all known. P is known, R is known, N is known. And then we find, and then if we solve this equation for P, maybe, I better, if we solve this equation, too much. If P is the unknown, right? Solving for P, uh, uh, and it's the reverse process of compounding, right? Fv over 1 plus R raised to N. And when you solve it for present value, principal, that's called the present value. And this is called the discounting. So I told you discounting and compounding are basically reverse processes of each other. They are reverse process of each other, right? Um, and from here, I gave you this, a secret. I mean, it's not a secret, but sort of like insight. The insight to solving any equation, right? It's basically identifying this z equals x times y structure. And if you can identify this structure, no matter how complex the equation may look, if you can identify, of course, you will need to simplify the equation to the best of your ability. I mean, if it is if it is reduced to the simplest form, then it's easier to identify this uh, uh, the fundamental structure. And then once you identify this, you can solve this for either x or either y, right? In other words, then x would be z over y will be z over x, right? So if you think about it, basically discounting is exactly solving this equation for p, which is z equals x times y format, and we're solving it for x. Now, the third question or third unknown that can arise from this is r, and that's quite plausible, right? We can all know, we can all tell. Um, for example, here's the example. you have $10,000 today and you put it in a bank for 5 years. And 5 years later, you want to have $30,000. So this is the target future value. So then, next question is, what should be the APR? What should be the rate, right? In order to grow 10K to 30K in 5 years, right? So that's quite a plausible question. Then how do we solve for that? How do we solve for R? Actually, you already know. You've already seen the solution already in topic one. You might wonder where in topic one. I mean, where did we see this? Does anyone remember where you saw? Does anyone remember in topic one that you saw this? Anyone? You probably might be having a hard time, but let's go back to in topic one. We had, we used house value example, right? In house value example, there were two scenarios, right? Scenario one and scenario two, right? And what's the difference? In scenario one, there is no additional income, only capital gains, right? In scenario two, there was capital gains and cash
flow.
Right? Additional income, right? Oh, excuse me. Okay, that's my doctor's office. Let me take this call. All right. All right. Sorry about that. I have doctor's appointment tomorrow, and so they were calling to confirm. So where was I? Um, so uh, in scenario one and scenario two, basically, what was the how is it related to this? Think about it. In that house value example, our focus was basically ROI, right? Return on investment. Return is what finance is all about. Um, so and basically, we started with holding period return, but then we had to come to a annualized return, because holding period can be different between from one investor to another. So it's not directly comparable. right? You cannot compare 10-year return on the 10-year holding period, asset that you were holding for 10 years, and you cannot compare it with an asset that someone was holding for 2 years. I mean, the entire holding period return or the total return cannot be directly compared when they are different. So we need to find out. We need to find how we find the. We needed to find annualized return, right? And in finding annualized return, um, uh, we have to use geometric average, right? We need to use geometric um, uh, because of compounding effect, right? Because anything that grows over time has, compounding effect. Uh, so it's not simple average. It has to be the geometric average. So the symbol for geometric average was G. Also, G is the symbol for growth rate. Now think about it. I told you in scenario 1, growth rate and return are the same thing. But in scenario 2, they are not the same thing. Not just that, but also not just that. Return is greater than just the growth rate. Why? In scenario 1, its growth is based on the capital gains, right? Growth is really, the average, return. When you find the average, geometric average of, capital gains, total capital gains, that's growth. And in scenario 1, since there is no additional income, that is return. Whereas in scenario 2, cannot be the same number because you have additional income. So basically, geometric average is the growth rate, and so you remember what the geometric average is? I mean, how you find geometric average? Does anyone remember? What was the formula for that?
You would take the last year, well, the recent last year, and divide it by the first year.
Yeah. And I mean, basically, the idea is the future value over present value, right? Raised to 1 over n minus 1, right? Of course, the future value is, that's the last year. I mean, the final year. In our example, think about it. We had, we bought the house in 2005 and sold it in 2016, right? Or 2015 or 2016. So 2016 is future value. I mean, from 2005, if you're standing in 2005, 2016 is the future value. It's the final price of the house because that's when you sold it, right? And then 2005 is the present value. So we did it like this, right? But then think about it. At the time, I told you I couldn't give you, I couldn't explain how this formula is derived, and because you were not ready yet, and at the time, so I just gave this to you, and you had to memorize. But the reason I'm doing this is so that you don't have to memorize anything, as long as if you can derive, I mean, from number 1, right? From the first formula, deriving the second formula is not difficult because they are basically reverse processes of each other. And then finding R, solving for R, that's also not a separate thing. It's all related. I mean, we are solving the same equation for R. So let's think about it then. Well, as usual, we start from the base formula, and the base formula, the base equation is future value is equal to P times 1 plus R raised to N, right? And then the problem we have now is that we can identify z equals x times structure, right? This is z equals x times y structure, but then that means this whole thing is y. Of course, this is x, this is z. But then our question is inside that y, right? This is the unknown. R is the unknown. And as you can see, I mean, there's no way we can directly isolate R, because think about it. It's like this is like the cage. Because 1 plus R is like the cage, and N is the padlock on the cage, right? N is the padlock on the cage. I mean, you cannot open the cage without opening the padlock, right? Without opening the padlock, you cannot open the cage. So you will need to, the first thing is, we need to isolate, since we cannot isolate 1 plus, we cannot isolate R only, we'll have to isolate 1 plus R raised to N, right? Because that's like a cage and the lock on it, they go together. So first, if we isolate, we will need to divide both sides by P, and we have 1 plus R raised to N, right? Again, N is the padlock, and 1 plus R is the cage, right? So how do we open that cage? First, we'll have to open the padlock. How do we open the padlock? To understand this, we need to refresh our memory on the exponents, right? The power functions, right? So I told you to download also the PDF file, and in the PDF file, there is basic refresher on the exponents, right? First of all, let's think about this. Product of powers, right? So a few let me look into a few so first of all, when the base is the same, right, x to the a times x to the b, it's x to the a plus b, okay? And x to the a over x to the b is x to the a minus b. So in other words, when the base is the same, the exponents can be added and subtracted when they are when these two quantities are multiplied or divided. And this is nothing to memorize because you can do some simple experiment. Just do a little, simple experiment. For example, this one, 2 squared times cubed, right? 2 squared times 2 cubed. We all know this is 4 times 8, which is, 32, right? Everyone can easily understand. But think about it. What is 32? 32 is 2 to the 5th, which is what? Which is exactly, right? 2 squared plus 2 cubed, right? 2 squared plus cube, right? The exponents. And also, the second rule, right? When you are dividing by something with the same base, right? Suppose you are doing this 2 cubed over 2 squared. We all know that's 8 over 4, which is 2. And 2 is what? 2 to the 1, right? Because it's just itself. But then, which is exactly, 2 raised to third power minus 2, right? So it's exactly, as it says here. It's not a difficult thing. Another thing, you all know, negative exponent, negative power, x to the negative n is the reciprocal. It's the reciprocal. It's 1 over x to the n, right? Not a difficult thing. And also, x to 1 over n, if, the fractional power, right? The power is in fraction, right? What does that mean? It's nth radical of x, right? Nth radical, or nth root. So a simple example. Suppose, we have x, first. X raised to half, that's square root of x. And of course, you might wonder, do we have to put this there? No, normally we just, omit it when it is square root, but it's not because the square root is not only for the square. I mean, that radical, the root symbol, that sign is not, the root operator is not only for square root, it's also for, for example, x raised to 1 over 6. What is that? Then, it's x to, it's the, sixth root or sixth radical. I mean, a simple, a practical example. Let's think about practical example. We know it's not a difficult thing, 4 raised to half, that's square root of 4. But then eight raised to 1 over 3, right? 1/3, 8 raised to 1/3. That's third root of 8. So we know it's 2, right? In other words, we can express anything like,
So is it like 8 and just square root that?
Third root, not square root. Think about it. Square means, it's, 2 times 2, right? Square means, literally square, because, square is, this is square, right? If you have x here, that's, x squared, right? The area is x squared. That's why we say square feet or square, whatever. But then, so if you have, 2 feet by 2 feet, that would be 4 square feet.
Oh, never mind.
Right?
Yeah, I see it in my calculator. Yeah.
And then if you have, but if you have a cubic thing, if you have a cube, right? There's 2 here, that means 2 here, the height, right? 2 sides are also 2, and the volume of this cube is 8 because it's 2 to the third, right? The whole thing is 2 to the third. But if you want to find the cubic root or third root of 8, then it should be 2, right? 2 times 2 times 2, because it's 2 times 2 times 2. So the bottom line is, right? We can also think about something like if we can express, x raised to 1 over n, whatever that n may be, that's nth radical or nth root of, right, nth root of x, okay? So just as just for an exercise, we can think of something like
so in other words, that's basically telling me how many exponents it would take to reach that number.
Right. How many, multiplication of x, how many duplication of x, or, how many
Right.
multiplication of x it takes. But what is this then? X to the negative 2. What should that be? X to the negative 2.
1 over
It would be
x
positive.
squared.
1 over x squared. Yes. Who was that?
Barry. Mukhtar.
Barry Mukhtar. Okay. Yeah. Mukhtar. Yeah. So yes. Today is what? Section 1401, and today is March 24th. Okay, Mukhtar, you're getting 0.5. Yeah. Also, we can say then, x to the negative n is 1 over x to the n, right? Again, another rule is power of power, for example. So we have, we can have, if we have x raised to a, that whole thing raised to b, again, we multiply both. X to the a times b. Okay. And then as a simple example, practical example, think about it. If we have 2 squared raised to the third power, that is 2. We already know, I mean, before applying that, 2 squared is 4, right? So 4 cubed will be 64, right? 4 times 4 times 4, right? But again, this is, 2 raised to the 6th power. It's 2 to the 6th power, right? Because 2 times 2 times, you don't have to, but 2 to the 6th power is what? You already know 2 to the 5th power is 32. So another 2, that's going to take it to 64, right? And 2 to the 6th power, that's 2 raised to 2 times 3, right? 2 raised to 2 times 3. So exactly, that proves, right? It's a verification of this rule. So this gives us, and what is this all for? If this is the important rule, right? This is the important rule that we need. Why? Now think about it. Because if we have x raised to n, and then if you raise it to 1 over n, in other words, we take the nth root of x to the n, then it will become x, because of that rule, right? It's going to be x raised to n times 1 over n. And what's going to happen? These two will cancel out, right? And then that's what? That is simply x, right? As they cancel out.
Simply because the 1 is there.
Yeah. I mean, anything, n times 1 over n will cancel out and it will become just 1, right? That's x, basically. So that is very important because it's the way to get rid of that exponent. In other words, we have brought this to this form, right? But now it is what? It's like z equals, it's not x times y now, it's like z equals x raised to y structure, right? It's x raised to the y structure. And what did I tell you? The key to solving any equation is to identify z equals x times y structure. What is z equals x times y structure? You can solve for x, or you can solve for y. Simply, z divided by y, or But then we brought it to this form, but it is not z equals x times y structure, but it's rather z equals x raised to y structure, right? But then how do we solve? And that what we want to solve for is inside that x. So we need to first open up the x. You understand? To open up the x, right? To open the cage, first you need to open the the padlock. You need to open the padlock. But then how do we open the padlock? We'll have to disenable that padlock. To disenable, the padlock is the exponent. So to disenable it, you just learned this is x to the y, x raised to y, but then you need to raise it to 1 over y. In other words, you will have to take the yth root of that x to the y. Right? Makes sense? But then you have to also remember, you must be mindful, because we are dealing with an equation, meaning equation means what? Left-hand side is held equal to the right-hand side. So if you do something to one side, you have to do the same thing to the other side as well. Otherwise, that equal sign won't hold. We need to keep that equal sign holding, right? We need to maintain that equal sign to hold. Otherwise, it's going to be that relationship will be destroyed, right? So without disturbing that relationship, right? Whatever we do to one side, we need to do to the other side as well. So what does that mean? To do that to the other side as well, that means we'll have to also take the 1 over y in the right-hand side. Okay? So then, now we understand what is going on here. Now let's get back to, just to make it simple, the left-hand side is what? We'll just call it the thing in the bracket, right? And the right-hand side, also let's call it the thing in the bracket. And we had n here, right? I know it's 1 plus r. I just don't want to write it every time. This is FV over P. To open the padlock is n. To open it, we'll have to raise it to 1 over n, right? And we'll need to do the same thing to the left-hand side, right? And then once that's done, then we know, I'll just abbreviate this as the thing in the bracket. And in the right-hand side, it will just become 1 plus r. And we know why. We understand very well why. Because this n and this n will cancel out. It's just going to be 1 plus r raised to n. 1 plus r raised to 1. 1 plus r raised to 1 is just, itself, 1 plus r. Right? Now, then what is our unknown? This is our unknown. We are trying to solve for this. So what do? We'll have to subtract 1 from both sides, right? We'll have to subtract 1 from both sides. Then the right-hand side will be, the left-hand side will be the thing in the bracket raised to 1 over n minus 1. Right-hand side will be r only. Now we have isolated r. So rearranging this so that, r will be on the left-hand side. It will be r equals FV over P raised to 1 over n minus 1. And voila, that's how we get that formula. Remember in topic 1, when I gave you that, where was it? When I gave you that formula, right? Yeah, I just, there was no time and no place to explain these the steps of derivation, because you are not ready yet, right? So you had to memorize that, right? You just had to memorize that. And this is exactly like scenario one. I told you in scenario one, growth rate is R. Because this is exactly scenario one, because you put $10,000 in the bank, and it, in 5 years you want it to grow to 50,000. So you have, no additional cash flow, no additional cash inflow. It's just the initial investment, and for it to grow to the target future value. So exactly, it's scenario one. So it's the growth rate, geometric average, right? That's how you found. That's how this formula is arrived at, right? So does that make sense?
Yes.
That makes sense. Okay, good. Yeah, at least one person. At least one person. I don't know about the rest of the class, but at least one
Yeah,
person.
I get you. I get it.
Great, great. The reason I'm showing you all this is because a lot of students, always ask me, Professor, do I need to memorize all this? All those formulas, do I need to memorize them? No, you don't. If you want to memorize them, fine. But if you memorize them, it doesn't last very long. After the semester, most of you, I mean, to always retain in your memory, you have to practice this all the time. But once the semester is over, once this class is over, you won't practice this, and then you forget. It's only natural. People, forget when they don't practice anymore. But if you know how they are connected, they are all interrelated. It's the same formula, right? Same equation, just solved for different unknowns, right? Different variables. But they are all related. But the problem of the current college education is college classes. They never teach you this. They just throw the formulas at you and tell you to memorize, memorize, memorize. And also in Excel there is prefabricated functions. You just enter, you just input the data, and it will give you the result. But then you never know how it works, and when something goes wrong with that, that black box, I mean, because you don't know what's going on inside, you just input the data, and when something goes wrong with the program, then you can't fix it. You can't do it, any other way. You don't know how to do it. But if you know how they are related, then without memorizing, you don't have to memorize. You can derive. Always, you can derive these formulas from the scratch, right? From the base formula. And I also showed you how this base formula is derived, also in topic 1, what compounding is. So knowing this, let's take a look at, it's what time? We have about 3 minutes, so we can do this. So let's go to row 18 and take row 18 is, it's obvious. You put, $10,000 principal in the bank today, and you put it for 5 years. So in 5 years, you want it to grow to 30,000. And what should be the APR? What should be the annual rate? We know what to do. All you need to do is, okay, let's do this together. Excuse me. Let's do this together, okay? You raise it to. I've been telling you that's the universal machine language for raising something to power, 1 over n. Now, our n is 5 years, and I would like to click it in. Normally, I can click it in, but when the formula is hanging above it, you can't click it in. So what do? You will have to type it in manually. Type it in C18. Okay. It's fun. There you go. You should have 24.57%. Did you all get that? Now, let's think about row 20. It's the same scenario. You want to grow your 10K into 30K in 5 years. But this time, compounding is quarterly. You see, M is 4. It's quarterly compounding. So we'll just need to make an adjustment. Okay, FV over P leads to 1 over, now, another parenthesis, because you'll have to multiply that 5 by 4. And then your T is where? In C20. So we'll type in C20. And you must multiply it by 4, which is in D20. Okay. Listen, you don't manually enter 5 or 4. You don't manually enter numerical data, because if you, that's called hard coding. If you enter numerical data manually, then that formula cannot be copied anymore, right? Because a fixed value is already in there. We want to copy that formula, right, over and over, so we don't have to solve every problem, one by one. Now, then you subtract 1 from it. Now think about it. And what are we going to get? We're going to get actually then quarterly rate, because this is all, adjusted for that M, right? The quarterly, compounding. So what you will get will be the quarterly rate. You might say, 5.65? Oh, we found it. No, you haven't found it yet. Why? The problem was asking for APR. The label is APR. So under the label of APR, if you leave it like this, you didn't get it right, because this is quarterly. So it's like either you are lying or deliberately, lying, or simply ignorant of the fact that, the problem is, originally asking for annual rate. So then what do you need to do? Because this is the quarterly rate, all you need to do is simply multiply that by 4, multiply, M to that, and you're going to get, so M is in D20. You'll simply, enter D20. The whole thing. On over, yeah. That's, okay. Why? Not a, what's that thing? Oh, F22. There was not, why did it have? It was 1. Why? Okay. The whole thing times D20. Why? Oh, I have to, okay. Yeah, that was why. That was why. Because this whole thing is the answer. This whole thing is the quarterly rate. You have to put the whole thing in the parentheses, right? Because this whole thing is the quarterly rate. Then times D20. Yeah. Now we got to the annual rate. So here we find that the remember previously I told you the higher the compounding frequency, the greater the future value. The greater the future value, right? So that means if we are getting at the same future value, right? Getting at the same future value, but different compounding frequency, and with a higher compounding frequency, the principal must be lower. For example, if here's the same example. the same future value, but this has higher compounding frequency, so the principal will have to be lower. And also the same logic, right? Same future value, same principal, but then it's same principal, same future value, then the rate will be lower. With the lower rate, even with the lower rate, you get to the same future value starting from the same principal, right? Over the same number of years because compounding frequency is higher, right? So that makes sense. I mean that. And then again, I've been telling you over and over, the simpler the model is, the better it is, because it's always true. If the system has more complex structure, something goes wrong, it becomes more difficult to find the source of the problem. And even if you find the source of the problem, it's more difficult to fix. Right? Think about it. If you have your car, even the car, I mean, there are many different cars, but fancy cars, usually if the fancy cars have, more intricate structure, intricate, construction, intricate, system, then it becomes a headache. It's a mess to disassemble it, and even to find the source of the problem, right? You have to disassemble, and you have to disassemble a lot. If the system is simple, you can easily detect the source of the problem, and you can easily fix it. So to make the model simpler, all we need to do is just add in two more columns. Just add in two more columns, right? And the column would the periodic rate and n. So in this example, the same example, we'll first find n, which is not difficult, 5 times t times n. There will be 20 quarters in 5 years, over 5 years. And then we simply then do find, this is periodic rate, so that's quarterly rate, FV over P is 2, 1 over N, which is in F5, which I could just click it in, but the proximity to that cell doesn't allow us. Then minus 1. Exactly, that's the quarterly rate we found before. And then to turn it into APR, all you need to do is multiply this by n. Then it turns into 22.59. We get to the same result. Okay. All righty. So it's about time. I mean, it's 2:57. So it's the right time to take a break. So let's take a 10-minute break and reconvene at 1:07 or 1:08. Okay. All right. If you have any questions, I'll take that after the break. All right. All right, we're back. We're back. So we have only one variable left now. Basically, we've done. So from the base formula, we got R. We know how to do R, right? Now the fourth one is okay. So where do I put 4? And the fourth one is n. So I'll put number 4 here, right? So what if n is the unknown? Yeah, it's also plausible assumption, right? Because we don't. What if we don't know n? The example was here. What if you know the APR is 24.57, right? The same scenario, right? You put $10,000 in the bank today. Currently, its APR is 24.57, and your target future value is 30K. So how long will it take, right? How long will it take, given the these 3 variables, right? How long will it take? How many years will it take to reach your target goal, right? So that's so then this is basically the problem is basically starting from this base formula, right? Why did I put it there? Starting from this base formula, we all know. And we know already, that there is no way we can directly isolate this padlock because the padlock goes with the cage, right? And this is, again, not the usual pattern, but it's not, it's z equals x raised to y format, right? It's not z equals x times y format, but z equals x raised to y format. So here's our new dilemma, because right now we can isolate this as far as Fe over P Fe over P is equal to 1 plus R raised to N. And again, it's exactly z equals x raised to the y. Then our question is, how do we solve for y? All right, this is the unknown. This is the unknown, right? To answer this question, we have to understand, we have to use logarithm, log, right? We have to understand what log is. What's a log or logarithm? Log is a way of expressing a large number, as the exponent of the base number. So in a way, it's a way of condensing a large quantity and express it by just by the exponent. So there are frequently, there are 3 types of logs that are frequently used. The first one is called common log, right? Common log. The second one is called binary log. Third one is natural log. Common log is, the most easy to understand. It's basically a log based on 10. So we all know 10 or 100 is 10 squared, right? And we can express this as, maybe I better, okay. So we can rewrite this, we can express this as log to base 10, log of 100 or 10 squared to base 10. There are two ways you can read this. You can say base 10 log of 10 squared or 100, right? Base 10 log of 10 squared, or log 100 or log 10 squared, log of 10 squared to base 10, right? Log of 10 squared to base 10, or base 10 log of 10 squared. But basically, this is 100. When you express it like that, in log, one benefit of log is that you can bring that exponent to the front so that it would look like 2 times base 10 log of 10 to base 10, right? So it becomes like it turns into, okay, it's already like that. So it turns into a z equals x times y structure. It becomes it turns into z equals x times y structure, right? And again, since log 10 to base 10 is 1. Think about it. Log of 10 to base 10, it simply means, that means 10 to 1, right? This means, 2 times 1, because log of 10 to base 10 is just 10 itself, right? Another way of saying this is 10 raised to 1, 10 to itself, right? So then obviously it is 2, right? Because it's 2 times 1 is 2. And suppose we have, we apply this to other numbers, like, what if it is, 1,000? Just 10 cubed, right? Through the same process, right? Base 10 log of 10 cubed, right? 3 times, right? Will be 3. This will be 3, right? And all of the other, numbers can be expressed that way. So in other words, even try 1 million, right? But it's easy when you are working with only the powers of 10. That's to 6, 10 to the 6th power, right? Will be 6. Even 1 billion. Why isn't it? Okay. Too far into the edge. 1 billion, right? 10 to the 9th. Nine. Right? 9. I mean, as long as it's the number is powers of 10, it's easy to visualize what it would be. And the important, this is the important property of log that we need from using log, right? Because the fact that you can turn it into, what did you do? We did, basically what used to be z equals x to the y, you turned it into log of z is equal to y times we turned it into y times log x. Now, in other words, we have it once again in z equals x times y structure, right? We turn it once again into z equals x times y structure. And once it is in z equals x times y structure, you can solve for anything. So therefore, here, then, and this is our unknown, right? Isn't that right? We had a structure like this. And in this structure, this was the unknown.
Padlock.
Yeah, the padlock. We want to isolate the padlock, right? We wanted to isolate the padlock. That's why we did this. And once we have transformed it to this, this is called, power function, whereas this is multiplicative function, right? Z equals x times y is multiplicative function, whereas z equals x raised to y is a power function. And to solve for, that exponent in the power function, we have to turn it into multiplicative structure. And if it is in multiplicative structure, then it's once again the same thing. We'll simply divide log z by log x, then we'll find that y, the padlock. But then here is a problem. It's not really, that simple. Why? Because can we use common log? Common log is the log that uses 10 as the base. It's not impossible. It's not impossible. But the problem is, think about it. What if it is a number like, what if the number we want to take the log of is 13.672? I mean, how do we know? Finding what this x will be is not easy, right? 10 raised to x. What kind of x will make this 13.672 the result of raising it to power, right? It's not impossible. I mean, mathematically, it's possible, but we need to use the computer or calculator to find it. But again, if the number here is some powers of 10. We can easily visualize, right? But it obviously puts limitations to the choice of numbers we can, turn into log, right? It's not that it is impossible, but it's just not easy to guess what that x will be. Now, the second commonly used log is called binary log. And the binary log is basically log using 2 as the base. So it's like, we all know 4 is 2 squared. So if we use, log of 2 squared to base 2, this will be 2, right? 8, that's log of 8 to base 2, which will be 3, right? Because we all know that's going to be, log 2 cubed to base 2, 3, right? 16, yeah, even 32, we know 64. Log of 64 to base 2, it's log of, 2 to the 6th to base 2, so it's going to be 6. Again, binary log is easy to use when the numbers we want to take log of is powers of 2. But when it comes to the numbers like some random number like this, binary log is kind of cumbersome. Next thing, third commonly used log is natural log. Natural log is the log using Euler's number E as the base. What is E? It's called Euler's number. It's not Euler, it's Euler's number. And Euler was a Swiss-German mathematician in German-Swiss or Swiss-German in the 17th century. And actually, there are like, 2 German mathematicians that made, great impact on, modern math. One is Euler, the other one is Gauss. And they lived around 17th century. I mean, they are not exactly contemporaries, but about 17th century, there was another great mathematician in France named Lagrange. So these 3 people, I mean, they are not exactly contemporaries. They lived around 17th century. So since Isaac Newton, Lagrange and Gauss and Euler, these people made great impact. So in honor of their heritage, we, some people pronounce it as Euler. No, it's like, even knowing that if you are either ignorant of their German heritage, or or you are deliberately, disrespecting their heritage, right? So if you anglicize, stubbornly anglicize everything, Gauss will have to be pronounced Gauss, and that's really Gauss. That's very gory, right? Lagrange will be pronounced Lagrange. And that is really stupid. Huh? The stubborn, just like Donald Trump, the stubborn, stubbornness, bigoted stubbornness, about what foreign is not, good for America. America first. Does that mean, anything of foreign heritage should be ignored and disrespected? But anyway, in honor of, their heritage, it's Gauss and Euler. Euler's number is an irrational number, just like irrational number, just like irrational fraction, just like irrational ratio, just like pi. There is no repeating part in the decimals. It just, all different decimal places, and they keep going infinitely. So there's no point in expressing it by number. This is represented by E. And also, natural log can be also written as ln of x. And no further explanation is needed. What would that n stand for? Natural log, right? And why natural log? Natural log has no limitations in, taking whatever number for log, right? We don't have time for natural log, at this point. First we'll have to discuss Euler's number, and then, it was all done in my main lecture, if you have watched it. But, what is the benefit of using log? Now, think about it. We had this, common log, and common log can be. Now, think about it. If you are measuring the distance between, very far distance, like, the distance between our sun and the nearest galaxy, which is, Andromeda galaxy. I believe it is, like 80 light years away, or, something like Andromeda galaxy. Uh, 80 light years away, and 1 light year is what? I don't even know. Like, one several billions of miles, or the 1 light year, the distance that light can travel a year, right? So suppose, so that's very far. And suppose, let's say the distance between the sun and our Earth, right? Let's say this is, 10 miles. Not 10 miles. 10, maybe, 10 billion miles. 10 billion miles, let's say, between sun and Earth. Then the distance between the sun and our nearest galaxy, Andromeda, is, let's say, 10 to the 12th, 10 to the 12th, 10 billion to the 12th. What does that mean? That means, if we obviously 10 billion has already what? How many zeros? 12 zeros behind 10. So 13 zeros, right? So 10 billion times 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 12 times, right? And if that's the distance, that alone will give you how many zeros? I can't even count, right? So like 12 times 12, 144 zeros. No, it's not just that. Yeah, 144 zeros.
Right?
Hmm? What's that? By zeros alone, right? 10 billion squared will be what? 10 billion squared is 13 zeros times 13 zeros. So that's 10 billion squared. So 10 billion to the 12th power is not just 13 zeros times 13 zeros. Right? I don't know. It's just unfathomable, or But so how do we express it in a limited space? Even if you have a stretchable, infinitely stretchable screen, it's going to take huge, but anyway, so then think about it. If we use just logarithmic scale, you're only used to a normal scale, but if we use logarithmic scale, that's going to be 1, 2, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, right? And let's say 13, 14. And here, 10 to the 12. So here, there's Andromeda. What does this mean? On a normal scale, 2 is 2 times 1. 3 is, 3 times 1. 4 is 4 times 1, right? The distance is just, but if we use logarithmic scale, on a logarithmic scale, log scale, 2 doesn't mean 2 times, it means 100 times. 3 means 1,000 times. 4 means 10,000 times. 10,000 times, right? In other words, like this, right? So 12 means, this means if the distance between the Earth and the Sun is, 10 to the 12th miles, that raised to 12, right? So that's, I was right. Then if it is like that, then you multiply, right? 10 to the 12 times, 12 times, 10 to the 12 times 12. That's, 10 to the 144th. 10 to the 144th. So this can be managed, right? I mean, such an infinitely large number can be managed within, within a manageable space. Otherwise, there's no way. I mean, only if you have, even if you have an infinitely stretchable screen, putting it on that infinitely stretchable screen alone is a huge task. I mean, you'll have to probably, you start from New York and stretch the screen all the way to LA. I don't know. Maybe, then you might be able to express that distance. I mean, each notch on this scale, each notch is, like 10 to the 12th, right, miles. 10 to the 12th is actually, a billion. 10 to the 12th is actually billion, right? So that's what the practical use of logarithm is. But again, as I said, we are we're out of time, so Euler's number and natural log, this needs to be reserved for our next class. Okay, alrighty. So any questions so far? Any questions? If you don't have any more questions, then I'll call it a day. The class is dismissed. I'm tongue-tied. The class is dismissed, and so you may be excused if you don't have any more questions. And I will stick around. I'll first stop recording and let you go and take your questions if you have any questions. Okay.